Alrighty, last time we left off with the Venn diagrams and whatnot. Do you remember that?
Mm-hmm.
Next, we have something called the counting rule. Very simple idea. There's something wrong with this. Okay, there we go. I can just write it over here, I guess. So counting rule is basically it gives you the number of possible outcomes, okay, of certain events. My mouse is acting up. So what does that mean? Let's say you can take 2 science courses, 3 math courses, and 4 English courses, okay? These are the possible possibilities that you can do. The question will be like, what are the total number of outcomes? Very simple idea. You just multiply all of them together. Here's the formula. Again, you can have multiple events. Here, there's 3 events, right? You just straight up multiply them. Here's a question. Suppose we toss a coin 3 times, right? How many outcomes are there? So if you toss a coin once, you have 2 outcomes. This is for the first coin toss. Second coin toss, you have 2 outcomes. Third coin toss, you have 2 outcomes, right? So in total, you have how many outcomes?
6.
No, you got to multiply them, not add them. It's m times n times k. So that'll be 8.
8.
2 cubed, right? 2 cubed will be 8. Everything here is almost the same. So here, look at this question. I'll just zoom in right here. I don't know what's happening. So this guy is trying to buy a car, and he can either choose 36 months, 48 months, or 60 months. It says how many outcomes are there, right? 3 events, you just straight up multiply. Wait a second. So this one's a little bit different because this is not the number of outcomes, right? How many events do we have here, actually? We have 3 different interest rates, right? We can call this I1, we can call this I2, we can call this I3. How many events are there? There's 3, yeah? And look at this. You can have a fixed rate and you can have a variable rate, okay? So there's 2 types. We can call this with a different letter. We can say this is K is 2. Basically what this means is you can either have 36 and 48, or you can have 36 and 60, and the last combination will be 48 and 60, like this. So this one's a little bit different than the one before. So these are the 3 possibilities, are the 3 outcomes that he can pick, right? Did we miss any? No, we didn't. So there you go. There's going to be 6 he can pick in this case. Because all 3 of them, like 36 and 60, you can pick this as your fixed and this as your variable. But at the same time, you can flip them around, right? So this one, it becomes 60 and 36, where this is the fixed and this is the variable interest rate. Yeah. So every combination of 2 numbers has 2 possibilities. We had 3 combos. 3 times 2 is 6. Okay, whatever. That's that for that. Well, let's look at something else. We're gonna look at this question. Again, it's not letting me pull it up. I don't know what the issue is. Anyways, we can just do it right here. So there's 60 males, 40 females, 100 total people that are interviewed. You see this? This is the number of possible outcomes for us. That's our n value. Now, if the question asked you, what's the probability of getting a male? What would be the answer? It'll be number of male, yeah? The probability of any event, look at this, the probability of any event happening, probability of A is the number of A divided by the total. So we have interviewed 100 people, right? What's the probability of getting interviewing a male? to be 60, because there's 60 males, divided by
over
100. So that'll be 60% or 0.60, yeah? Don't know why this is automatically moving. Okay, whatever. That could be one question. Find the probability of male. Oh, look at this. Things are going to be different. What if the question asked you, what's the probability of interviewing a male, yeah? But at the same time, he is in favor of whatever this is. Now we're looking at male and in favor, right? For this one, again, the total is still going to be 100. It's not going to change. But how many males are there that are in favor of whatever this is?
15.
Yeah, so it's going to be 15 over 100. What if I asked you female and against? Female and against.
36 over 100.
Yeah, exactly. So when it says and, we're looking for the intersection, okay? When it says and, we're looking for the intersection denoted by an upside down EU. Cool? On the other hand, right, look at the difference. Probability of male and in favor was 15 over 100. Now the question could ask you, what's the probability male, and instead of being an and, it'll say or in favor. Basically, we're trying to find, if you from a Venn diagram approach, this is male, this is in favor, right? They intersect. In the middle, we have 15. How many do we have here? This is male, this is in favor. There's 60 males. If 15 is in here, this will be 45, yeah? How many in favors are there in total? There's 19, so this right circle is 19. What's this part inside? 4, right? See this? Has to add up to 19. So if there's 15 in the middle, that means there must be 4 over here. Look at this question. It's asking us, what's the probability of being a male or in favor, right? Or in statistics, it means this. You need to find the total of the circle right here. If you straight up add them up, look at this. You get 60 plus 19, you would have gotten 79 over 100. But the thing is, you can't straight up add them up because it's not going to be 79. Let's see what it actually is. It'll be 45 plus 15, which is a 60, plus 464. So the probability of it getting a male or in favor is going to be 64 over 100. You can straight up add them up, okay? If you want a formula approach, I'll show you both approaches. Let's say we're trying to find probability of A or B, right? Any event A or B, it's going to be A, probability of A, plus probability of B, minus probability of A and B. So if you use this approach, the probability of getting a male is 60 over 100. The probability of being in favor is 19 over 100. Minus, what's the probability they both have in common? 15 over 100. You do this, you're going to get 64 over 100. Cool? So that's the difference between and or. Or means you're looking for the sum of the Venn diagram, the circles in the Venn diagram. Whereas and means you're looking for where they intersect. What else have they got? Not any good questions. We'll talk about this in a little bit. Next, let's talk about something called mutually exclusive. It's a very simple idea. If two events are mutually exclusive, what they have in common is nothing. They have nothing in common. The formula approaches this. Probability of A and B, what they both have in common is 0. The Venn diagram approaches this. You have a circle of event A here. You have a circle of event B here. Do they intersect?
No.
No, they have nothing in common, right? If they have nothing in common, it's called mutually exclusive. Cool?
Mm-hmm.
And if they have something in common, like we had in the previous question, if they intersect anywhere, they're not mutually exclusive. It's a very simple idea, this one. Okay, let's look at this one. So we have a dice roll. A represents getting 2, 4, 6, B represents getting 1, 3, 5, and C represents 1, 2, 3, 4. Are they mutually exclusive? A and B. Are A and B mutually exclusive? Right? A is here, B is here. A has 2, 4, 6. B has 1, 3, and 5. They don't touch anywhere, right?
Mm-hmm.
So yeah, they are mutually exclusive. What about A and C? Does anything intersect between A and C?
2 and 4.
Yeah, so 2 and 4 intersects. 2 is going to be in here in the middle. 4 is going to be in here in the middle. A has 6 by itself remaining, and C has 1 and 3. The fact that they do meet in the middle means A and C are not mutually exclusive. In other words, what they have in common is going to be equals to 0. Cool?
Mm-hmm.
This one is a word problem now. It says Y is the event that the adult has shopped on the internet at least once, and N is the event that adult has never shopped on the internet. It's asking us, are they mutually exclusive? What do you think?
Yes.
Yeah, they are mutually exclusive. They have nothing in common, right?
Mm-hmm.
It's two different circles in a Venn diagram. Cool?
Mm-hmm.
The next thing to talk about is independent and dependent events. What does this mean? We kind of talked about this when we drew the tree diagram. Let's say you're tossing 2 coins. Does the result of the first one have any effect on the result of the second one?
No.
No, right? They're independent. If the results does not influence the probability next, they're independent. Coin toss is the perfect example of something being independent. Where something being dependent is the one that we did with the toys in a bag, right? Let's say there's 5 red toys. Let's say there's 10 total. The probability of getting the first red toy is 5 out of 10. We're not putting this back in. What's the probability of getting another red toy? 4 out of what? 9.
Mm-hmm.
This is the first pick. There's 5 red toys out of 10, 5 over 10. Now for the second red pick, we've already picked out a red, so 5 becomes 4. And we already picked out a toy. That means the total 10 becomes a 9. Are these independent events or are these dependent events?
Dependent.
Right. The fact that whatever you picked here is going to affect the probability in the next pick means they are dependent events. Okay.
Mm-hmm.
Look at this notation here. It says probability of A. You see this middle straight line in the middle? That is not divided by or like an absolute value function or anything. That means given that. The probability of A, given that B occurred, okay, that's how you read it, is equals to probability of A. Did B have any influence on A in this case?
No.
No, right? So let's say probability of A is 0.2, probability of B is 0.8. The fact that probability of A, given that probability of B happened, is still 0.2, right? Look at this. Did B influence A at all?
No.
No, it did not. That means A and B are independent. Okay. We don't care if B happened or not. The probability of A never changed. So it does not influence B. These two events are independent. Same thing on the other side. Probability of B given A is PB. That means doesn't matter if A happened or not, it does not influence B. These are both independent, okay? Independent events because there's no influence. But if this changes, right? If this changes, instead of 0.2, it becomes 0.1 or something, this means B influences A. Those are dependent events, okay?
Mm-hmm.
Here it says, are events female and in favor? Where's this table? Whatever, we'll pick a different question. Let's do this. A box, so there's 100 CDs in a box, and they were manufactured on 2 different machines. 60, so this is what happened. There's 100 total. 60 of them were on machine 1. And that means 40 of them would be on machine 2, right?
Mm-hmm.
From machine 1, 15 are defective. Actually, no. Now there's a lot of things that's going on here. So 15 of them are defective. There's a lot of words. So we'll just start denoting everything. N is gonna be 100, okay? Probability of defective, there's 15 defectives, right?
Mm-hmm.
Out of 100 total, so that's gonna be 15. Machine 1, there are 60. And look at this, of the 60 CD that were manufactured in machine 1, 9 of them are defective. So look at the notation. Probability that the thing is defective, yeah?
Mm-hmm.
Given that it came out of machine 1 is equals to 9. Okay, it's going to be 9 over 100 if you're looking for probability, but defective given machine 1. 9 of them were defective given that it came from machine 1. What's the question actually asking us? It's asking us, let D be the event that a randomly selected CD is defective, and let A be the event that it was manufactured on machine 1. So we can just write I as A, because that's what they do. Now the question is, are D and A independent? What do you think? All you have to do is check this. To answer this question, check. Is probability defective as it is this equals to probability of being defective given that it came out of machine 1? Are these two probabilities the same or not, right? We already know the right-hand side of this. Probability of D defective given that it's coming out of machine 1 is 9 out of 100. There's 15 defectives. The total was 100. What's the probability of D?
15 over 100?
Yeah, 15 over 100. Are these two equal?
No.
No, they're not. So did A influence the D?
Yes.
Yes, it did. Independent or dependent?
Dependent.
Yeah. Next, let's look at something. Oh, don't know what's happened with this guy today. Next, let's look at something called complementary events. We kind of talked about this a few days ago as well. Very simple idea. There's a circle in the middle. Complement event is anything that's inside the rectangle, but not inside of the circle, okay? Do they
Mm-hmm.
have anything in common?
No.
No, they don't. So are they mutually exclusive?
Yes.
Yes, they are. In terms of probability, it's going to look like this. Let's say probability of A is 0.1. Complement event is denoted by this bar thing up here. A bar means the complement of A. That will simply be 1 minus 0.1. This will be 0.9. Let's say A, there's 20 A's. Let's say the total is 100. What's A bar? It'll be 80, right? What this means
Mm-hmm.
is A is here with 20. A bar is outside here. That there's 80 A bars. Cool?
Mm-hmm.
Okay, this one's asking us for probabilities. So there's 2,000 taxpayers. We can say that's our total. N is 2,000. And we can say the people that have been audited, those are 400. If one taxpayer is randomly selected for this group, what are the two complementary events? And what are their probabilities, right? The first complementary events is that you have been audited. What's the probability of being audited? Something over,
2,000.
look at this, 400 over 2,000. These two zeros cancel out with these two zeros. 4 over 20, that's 1/5, it's 0.2. Okay.
Mm-hmm.
So what's the other event? I mean, the other event is that you're not audited, denoted by the complement event PA bar. What will that be if PA is 0.2? 0.8, okay?
Mhm.
Complement probability wise, it's just gonna be always 1 minus. You can also look at it this way. If A is 400, that means A bar is gonna be 2,000 over 400, which is 1,600. Probability of A bar will be 1,600 divided by 2,000, which is 4 over 5, 0.8. Cool.
Mm-hmm.
So those are complementary events. Let's look at the next question. In a group of 5,000 adults, so let's say N is 5,000, 3,500s are in favor. So let's say favor is 3,500. 1,200 are against. So let's say some event A is 1,200, and 300 have no opinion. Let's say we can say what, and again, these letters are arbitrary. You can call them whatever you want. I'm just going to call them B. B represents no opinion. Okay, 300. One adult is randomly selected from this group. Let A be the event that the adult is in favor. That's going to change our notation. So A is in favor. That's it. Any other things? No. And then 1,200s were against. So we can say this is B, against. And we can say C, have no opinion. What is the complementary event of A? If A is the event that they're in favor, right?
Mm-hmm.
What is the complement? Right? A is in favor. Yeah, what's the opposite of in favor?
Not in favor.
Right. Not in favor, or in this case, I can remember there's 3 events here. So this is A, right?
Mm-hmm.
Complement means anything that's outside of the circle. If there's A is inside, that means B and C are outside. Not favor is B, but the fact that C is also outside, that means it's gonna be anything that's not A. There's 1,500 of them, right?
Mm-hmm.
3,500 A, that there's gonna be 1,500 of them. And you just do 35 over 5,000, 1,500 over 5,000, and that's it for that. Let's look at this question. We can do 45 and 46. How many different outcomes are possible for 4 rolls of a die? Look at it this way. 1 die, 1 roll, yeah,
Mm-hmm.
has 6 possibilities, right?
Uh-huh.
1, 2, 3, 4, 5, 6. The second roll also has 6 probabilities or outcomes, but they can all stem from each individual number. Look at this, you can get 1, 1, right? You can get 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. Same thing is going to happen from 2, like that. Same thing from 3, 4, right? There's going to be 36 possibilities just on the second. For the third, again, from each 36 of these, there's going to be 6 more. For the fourth, from all 108 of them, there's going to be 6 more, like that. So it's gonna be 6 to the power of 4 will be the answer. Whatever that is, for 4 rolls of a die. Coin toss is very similar. The first one you have 2 outcomes. The second one you can have 2 more, right? Third one you can have 2 more. So out of 10 coin tosses, what's the total number of outcomes?
2 to the power of 10.
Yeah, that's it. 2 to the power of 10. Let's look at this one. We have event A 257, event B 248. Are events A and B mutually exclusive?
They're not.
No, they have 2 in common, right? So they are not mutually exclusive. B, are A and B independent events? So there's A total numbers. Both of these have 3 numbers, right? And it says it's equally likely. This one, yeah, we have no inclination that they're not dependent. They have to be independent. C, what are the complements of A and B? Look at this. If A is 257, A bar will be anything that's not A, right? It's gonna be 1. What else? What's A bar? It's gonna be 1.
3.
Yeah, 3, 4, 6, right? There's 4 events, and it's asking us for their probability. The probability of A bar will be 4 over 8, because there's 8 total. Yeah? Same thing with B. There's 3 here. That means anything that's not 2, 4, 8 will be B, and that means it's gonna be 5 over 8 for B. Cool? Look at 449. An ice cream shop has 10 flavors and 5 kinds of toppings. And it says, what are the total number of outcomes? So you can have 10 different things. And out of each 10 different things, you can put 5 different toppings, right? So using the counting rule, how many outcomes are there in total? 50. Yeah? You can have 1. Let's say it's 1 to 10 are the flavors. And let's say 11, again, these are, you can denote them with letters or whatever, to 15 are the toppings. You can have either 111, 211, 311, right? There's going to be 10 of them, and you can do that 5 different times. You can have 112, 212, there's 5 of them, so 10 times 5, 50. A man has 4 suits, so he can either go with suit A, B, C, D. 8 shirts, so out of each suit, he can have 8 different options, right? Like that. And then finally, from each shirt, he has 12 different options. The question is, how many total outcomes are there? What do you think? What times what times what?
4 times 8 times 12.
Yeah, and that's it. 51 is the same thing. 4 soups, so it's going to be 4. 8 types of main courses, so 8 times 4. 5 kinds of desserts, so times 5, and 6 kind of drinks. Just multiply all of them together. Cool? These counting rule problems are pretty simple. Let's look at 453. It says if one adult, the total is 2,000. It says right there, total is 2,000. He has never shopped on the internet. How many people have never shopped? 1,200 have never shopped on the internet, right? 700 plus 500, 1,200. So for I never shopped on the internet, it's just going to be 1,200 divided by 2,000. Cool?
Mm-hmm.
Second one is a male. How many males are there?
1200.
Males, there are also 1200, yeah. So there's 1200 males, and total is again 2000, so it's going to be 1200 over 2000. Part 3 has shopped on the internet given that this adult is a female. Now look at this. The probability of being a female is 300 over 2000, right? Actually, no, it's not 300, it's 800 because there's 800. Probability of female is going to be 800 divided by 2000. Yeah.
Mm-hmm.
So the probability of being a female is what? 8 over 20, 2 over 5. Probability of being a female is 2 over 5. And what else do they want? Shopped on the internet. What's the probability of shopping on the internet?
800.
800. It's the same, right? It's 800 divided by 2000. For this one, we haven't seen it yet, but we're going to use a new formula for something called given that. For conditional, this is called conditional probability. You can draw the Venn diagram, but it can get tedious really quickly. If you know this, it might be better. It works like this. Probability of A given B happened is equals to probability of A and B divided by the probability of B. So the probability of being a female is, we did this, it was 2 over 5. The probability of shopping on the internet is also 2 over 5, right?
Mm-hmm.
What's the probability of being a female and shopping on the internet? Female and shopping, you see, and means where they meet.
Uh-huh.
It's going to be 300 over 2000, which will be 3 over 20. Okay.
Mm-hmm.
Now we're going to use this formula. What do they want? Has shopped on the internet given that it's a female. We're looking for this. Probability shopped given that it's a female. Using this formula, look at what this becomes. B comes in the denominator. That means F is going to come in the denominator. And you see this given sign becomes and. Same thing here. It's going to become probability of S and F, like that. S and F and S, these two, they mean the exact same thing. A and B and B and A mean the same thing. So we have 3 over 20 on the numerator. And on the denominator, we have 2 over 5. Does this 5 go to level 1 or level 2? It's going to go all the way to the top. Here's the proof. It's divided by 2 over 5. It's going to be 3 over 20 times 5 over 2. Yeah, it'll be 15 over 40. And that's the answer for part 3. Conditional probability. We haven't seen this yet, but this is what you would use. Don't worry too much about this. We'll see this more as we go along. We're going to use the exact same formula for part 4. Is a male, right? So probability is a male given that this adult has never shopped. So we're trying to find male given that he has never shopped, means the complement event of shop. What's the probability of being a male? 1200 over 2000. What's the probability of shopping on the internet? It's also 1200 divided by 2000. If PS is 1200 over 2000, what's PS bar?
Isn't it 800?
You're right. It's not 1200. It's 800. It's the sum of these two. So what's the probability of PS bar if PS is 800 over 2000? It's gonna be 1 minus that, 1200 over 2000, right? If 800 out of 2000 have shopped, that means 1200 out of 2000 have never shopped. And what's the probability of being a male and not shopping online? Me,
700.
yeah, 700 over a 2000, right? Like that. And again, we're going to use the exact sum formula. Male, given that never shopped, it's going to be probability of male and never shopped divided by probability of never shopped, like that. Now we have everything we need, I think. It's going to be 700 over 2000 for the numerator, male and never shopped. And never shopped was 1200 over a 2000. These two 2000 cancels out. The answer is 700 over 1200. In other words, 7 over 12 for part 4. Cool? That makes sense? Conditional
Yes.
probability. You just need to know a couple of formulas for stats. That's how it is in most cases. Once you go beyond the graphs and whatnot. B. Are the events male and female mutually exclusive? Can you be, do they ever intersect? Follow the males. Males going this way, right? Females going this way. Do they ever intersect?
No.
No, so they are mutually exclusive. What about half shopped and male? Half shopped is going down this column. Male is going across this row. Do they intersect?
They do.
They do, right? There's 500 people that are male that have shopped. So that is not mutually exclusive. Cool. C, are the events female and shopped independent? All right, the probability of shopping online was 1200 over 2000, right? The probability of being a female was 800 over 2000. Now let's do this. The probability of being female, given that they shop online, okay? The formula is this. Again, PA given B is probability of A and B on the top, A and B on the top, divided by probability of B. So F given S would be where F and S meet, which is 300, divided by S, how many people were shopping? 1200. So that is 1 over 4, okay? The PF is 2 over 4. The fact that female given shopping is not equals to female, probability of female, means this event influences F, yeah? See, this is 1 over 4, F given S, and F was 2 over 4. The fact that these two are not equal means they are not independent, okay? They are not independent. I don't know why they don't give us the totals, which is annoying. So let's write the totals here first, because we're going to need it. Or maybe they do. They give us the total, which is 1012. But we're going to add them across to make our lives easier. So this is 509, 258 plus 245. This is 503, 381 plus 258. This is 639. And then finally 128 plus 245. That is 373. All right. Part A does not favor the use of nuclear power. What's the probability? Does not favor. We don't care which party they are.
373.
Yep, so it's going to be 373 divided by 1012. Second one, is a Republican.
$509 over 10.
Yeah, 509. Part 3 is going to be tricky. It says favors the nuclear. So we're going to go probability favors given that they are Republican. Okay, like that.
Mm-hmm.
The formula again is this: A given B becomes A and B on the top divided by B. What's the number of people? What's the intersection between F and R? F means this, R means this. What's the intersection? How many people favor and they're Republicans?
381.
381. That's going to be our numerator. Or you can write it as 381 over 1012. That's going to be the probability. What's the probability of being a Republican? It was 509.
509.
Yeah, over 1012. So you see these two cancels out. So the answer favors the use, given that it's a Republican, is 381 over 509. Okay.
Mm-hmm.
What about part 4? What is that asking us? It's asking us, you're a Republican, given that you don't favor. Yeah.
Mm-hmm.
Okay, what's the intersection between R and F bar? F bar just means does not favor.
128.
128. How many F bar? Again, look at this. B goes in the denominator. You can write 128 over 1012. That'll be the probability. What's F bar? What's the probability of F bar? Because that goes in the denominator.
373.
Yeah, 373. Again, you can write the totals if you want like that, but they're going to cancel out anyways. So this is the answer, okay? Republicans, given that, not favor. B, are the events favor and does not favor mutually exclusive? Do they ever meet? Look at favor and do not favor. Do they ever meet?
No.
No, they don't, right? Because this is going down this way, this is going down this way. These are what kind of lines? Parallel lines, yeah? They'll never
Mm-hmm.
meet. So they are indeed mutually exclusive. They never meet. What about does not favor and Republican? So we're going this way and this way. Do they ever meet?
No.
They
Oh,
do,
they
right?
do.
They do. 120 of them do not favor, that are Republicans. That is not mutually exclusive, okay?
Mm-hmm.
C, are the events does not favor and Republican leader independent? Should not have erased it. Does not favor was, what is this? 373, I think. 128 plus 245. Yeah, so does not favor is 373. And Republican was 381 plus 128. That was 509. Question's asking us if these two events are independent or not, yeah? We can do this multiple ways. We can do it like this. The probability of F given R, if this is equals to the probability of F bar, these are going to be independent. These two events are going to be independent. If they're not equal, they're not going to be independent. Where no PF bar, that's going to be 373 over 1012. Let's find PF bar given R. Again, this is a formula, A given B. On the numerator, you get A and B, and the B goes in the denominator. How many people, what's the intersection between F bar and R? Because that's what goes in the numerator.
128.
128. What's R? How many R's are there? 381 plus 128. There are 509 R's. So that goes in the denominator, okay?
Mm-hmm.
It's kind of hard to see if these two ratios are the same. I'm going to convert them into decimals by plugging it in the calculator. 128 over 509 is 0.251, and 373 divided by 1012 is 0.368. They are not equals to. Does that mean they're independent or does that mean they're dependent?
They're dependent.
Right. If they were to be equal, they would be independent. As of right now, they are dependent. Cool.
Mm-hmm.
All these questions are the same. Which one am I looking at? I'm looking at this one, 461. So a company hired 30 new grad students, new college graduates. Okay, so N is 30. There's total 30. Of these, 16 are female. So I'm just gonna write that as F because I don't think we need probabilities, no. So there's 16 females and 11 are business majors. Of the 16 females, 9 are business majors. Look at this. Business majors, given that they're females, is 9, okay?
Mm-hmm.
Are the events female and business major independent? Or are they mutually exclusive? I mean, business majors and females, they intersect, right?
Mm-hmm.
Are they mutually exclusive?
No.
No. Now to check independence, look at this. B given F is 9, whereas B by itself is 11. Are they independent?
No.
No, they're not. They're dependent because F influenced B, right?
Mm-hmm.
If they were independent, both of these numbers will be the same. In this case, they are not the same. Let's look at this. Let A be the event that a number is less than 3 if we roll a die once. Less than 3 means you can either get a 1 or you can get a 2, right?
Mm-hmm.
The probability of getting a number less than 3 is what?
2/6.
Yeah, 2/6. What is the probability of A? Well, it's 2/6. What is the complement event called of this? It'll be getting a number more than 3.
Above
More
3.
equal to or above 3.
Mm-hmm.
Okay, that'll be the complement number. If this is A is 2/6, that means probability of A bar will be 4/6. Because you can get 3, 4, 5, 6, but divided by 6. And that's it for that. Easy peasy. Next one. The probability that a randomly selected college student attended at least one major league baseball game last year is 12. Okay, so this is our event. College student attending MLB game, baseball game. What is a complementary event called in this case? It is a college student that didn't attend any baseball games, right?
Mm-hmm.
Our event right now is college student attended at least once. That means the other event is college student attended none or 0. If this probability is 0.12, what's the probability of its complement event? Remember, they always add up to 1. To get the other, you just do 1 minus. It'll be 0.88. In other words, 1 minus 0.12, 0.88. Cool?
Mm-hmm.
That's it for complement. Complement, you just do straight up 1 minus or n minus, whatever. Intersection, we've talked about this a few times. It's where they meet in the middle, denoted by an upside down U. And this is the formula that we use. It's coming right here, but this is what we used last time. So probability of B given A, right? It's going to be probability of B and A. And whatever comes second is always going to come in the denominator. Last time I wrote it as A given B. That's why B came in the denominator. Now, if you want to find B given B, it's going to be A in the denominator, which is the same thing as this if you divide both sides by this. All right, so let's look at this, and good thing they've given us the totals as well. What is the probability that the employee is a female, okay, is a female and a college graduate? It's going to be something over something.
4/40.
Yeah, 4/40. Let's try this one. I don't know what they're finding there. A box contains 20 DVDs, 4 of which are defective. If 2 DVDs are selected at random without replacement, what is the probability that both of them are defective? We can draw a tree diagram for this one because I guess that's what they did in the previous one. Let's try this way. So there's 20 total here. 4 of them are defective, right?
Mm-hmm.
How many of them are not defective? 16.
16.
16 is going to be D bar. Now, what's the probability of selecting a defected on the first try? 4/20. Okay.
Mm-hmm.
Now, given that this was, we're not putting it back. It says without replacement. What's the probability of selecting another defective?
4/20.
No, it's not going to be the same. It's going to change because we're not putting this back in.
Oh, 3/19.
3/19. That's going to be the answer. 4/20 times 3/19. Whatever that is on a calculator. 4/20 times 3/19. There we go. Are these dependent? Were those two events dependent, D1 and D2?
Yes.
Yes, they were, because the probability changed. It was influenced, right? It was indeed dependent. Let's look at this one. The formula is given up there. The probability that a randomly selected student from a college is a senior is 20. So probability of senior is 0.20. And the joint probability that the student is a computer science major and a senior is 0.03. Joint probability just means this one, the intersection. So we have S and computer science, senior and computer science is 0.03. Find the conditional probability that the student is a computer science major. So we want to find C given that he is S, like that. Okay.
Mm-hmm.
What's going to be the formula? Again, you can follow either one of them, right? Look at this. A given B becomes A and B. So we have C and B on the top, the joint probabilities. And does S come on the bottom or does C come in the bottom?
C comes at the bottom.
No, look at this. This guy comes in the bottom. Whatever comes after the line, right, comes in the bottom. B given A, he comes. A given B, B comes. C given S, S is going to come. Like that. Not C.
Okay.
And we didn't even have C, so it must have been S. And we already have the two numbers. It's going to be 0.03, should have been an S, divided by PS is 0.20. So 0.03 divided by 0.2, it's going to be 3/20. Okay? That's the probability, that's the conditional probability that a science major given senior. 3/20.15. Let's look at the next idea here. An office building has 2 fire detectors. The probability is 0.02 that any of these will fail to go off during a fire. That's probably still too high, right? There's a 2% chance that the fire alarm doesn't go off. Find the probability that both of these fire detectors will fail to go off in the case of a fire. See, the formula is right up there. Yeah? We have the first one, which has a 2%, and it says both of these. So you have the second fire detector, which is also 2% or 0.02. And the question is asking us to find the probability of A and B. So it's going to be 0.02 times 0.02. Okay? That's it. And it's not 0.04. It's going to be 0.0004. You can plug that in a calculator. $427 is going to be, look at 427. The probability that a patient is allergic to penicillin is 0.20. Okay. Suppose this drug is administered to 3 patients. We can draw a tree diagram for this, but you don't have to. You can use the formula before, but just to show you. Let's say penicillin and not penicillin. This is 0.2. Does the first guy being allergic have any influence on the second guy being allergic?
No.
No, right? They're independent. So the second guy is also going to be 0.20. The third guy is also going to be 0.20. It says find the probability that all three of them are allergic. It's going to be 0.20, 0.20, 0.20, multiply all of them together. It's going to be 0.20 cubed for part A. Okay.
Mm-hmm.
Part B, it says at least one of them is not allergic. At least one of them is not allergic. Okay. This is our sample space. P bar, and we got to go one more level deeper. It's going to be, you can see it's going to be PPP. They're all allergic, or you can go PPP bar here, or you can
Mm-hmm.
go PP bar P. Last one will be P bar P bar. We're done with the top half. Now at the bottom we have P bar PP, P bar PP bar. We're done with this. Next one will be P bar P, and then finally P bar P bar. What does it say? It says at least one of them is not allergic. Okay, not allergic means P bar. At least one of them is not, yeah?
Mm-hmm.
So how many of these have at least one? 7 of them, right?
Uh-huh.
So the answer to this question, at least one of them is not allergic. What you can do is you can follow this tree 7 different times, or you can use the idea of a complement event. Probability always needs to add up to 1. So when we add up these 8 events, they always add up to 1. We already know the answer to part A. The answer to part A was 0.2 cubed, yeah? That
Mm-hmm.
means the sum of 7 of these is going to be 1 minus 0.2 cubed, whatever that is on a calculator. And that's way quicker than having to do this 7 different times, right? So this
Mm-hmm.
is one of those cases where knowing the idea of complement events is really good. All right, let's call it a day there.
Okay, thank you.
See ya.